Thank you. So I want to start just recording the definition of a sofic group that we have seen last time, or actually maybe already in the first talk. So let gamma be a finitely generated group. And let's pick a surjection from the free group on D generators onto gamma. Then I said that gamma is sofic if and only if there exists a sequence of homomorphisms from the free group on D generators to symmetric groups on some finite sets. I now just take some numbers kn, so these are homomorphisms, such that two conditions are satisfied. So first of all, as n tends to infinity, the Hamming distance computed in this symmetric group, so I will write dkn of phi n of g to the neutral element. This is supposed to tend to 0 for all g which lie in the kernel of pi. So that was the first condition. And the second condition is as n tends to infinity, the Hamming distance of phi n g to the neutral element tends to 1 for all g which do not lie in the kernel of pi. Right? So this is basically some sort of statement that it's kind of well defined on gamma, and this statement here says that it's kind of injective on gamma. Right, and so that's maybe a bit hard to work with sometimes. So an equivalent formulation, then that's really what I want to mention, is the following. So if S from gamma to Fd is a section, so that means it splits this surjection, then we can construct maps directly we construct maps phi n, and they are defined to be psi n to be phi n composed with S. So these are now maps which are defined on gamma, right? And they satisfy, well, similar conditions. So first of all, if you now compute the Hamming distance, I mean, they will not be homomorphisms anymore because S is not a homomorphism, right? But they will be almost homomorphisms because S, you have seen here, on the kernel everything will be almost trivial, right? So that means that psi n of g, psi n of h will be close in the Hamming distance to psi n of g times h. So this will tend to 0 as n tends to infinity, and the second condition is basically unchanged. So psi n of g, the Hamming distance to the identity permutation, this tends to 1 as n tends to infinity for all g which are in gamma, but of course not the neutral element, right? For the neutral element, you will have, it's not tending to 1. Right, so this maybe is a bit more familiar, and so I just encourage you to see that just do this exercise to show that these two characterizations are actually completely equivalent, and it's sort of very easy computation. Okay, so maybe the second description anyway is one which is a little bit easier to understand, because these are maps which are directly defined on the group, and you now see that you really want to model the group law that you see on gamma by permutations. And since this is really pointwise convergence for each individual pair GH, this is really a local property. So you basically only consider a finite window of the group multiplication table at a given time, and you want to find permutations which do exactly the same thing up to little mistakes in the Hamming distance. Right? So from this description, for example, it's completely obvious that if the group is residually finite, then of course it will be sofic, because you can just take the finite quotients and use the permutation representation of these finite groups to see that this definition is satisfied. So this is also very easy. So how would one could one possibly try to construct a non-sofic group, right? Something that violates this definition. How, I mean, could one try to construct a non-sofic group? Right, so let me give you some like kind of very naive approaches and tell you that this particular cases it does not work, right? But still, sort of the machinery that goes into these ideas, I mean, maybe it's, if you have a slightly different approach, maybe you can make this work. So this is actually just some general strategy that I want to present. So first of all, if it's not a sofic group, then well, it cannot be residually finite, so there must be some problem. So this group must have problems mapping to finite quotients. Right? So there are some elements which always die if you map them to a finite quotient. And that's something that is well studied. So this is goes under the name of the quasi-variety of finite groups. So you look at non-trivial implications that only hold for finite groups, but not necessarily for infinite groups. So let me give you an example. Right, so let me give you a very easy example that holds for all groups. So like if for example, A is the neutral element and B is let's say anything, then also BA, B inverse, A inverse, right? Well, not this will be the neutral element, right? This is sort of completely trivial. But now that holds for all groups. But the interesting thing is that there are implications of that form that hold only for finite groups. And they are, of course, a little bit more complicated to find, right? But let me give you an example. So the example that I want to give you is the following. So if you have two elements in a finite group that satisfy this equation that I've written here, then this can only be if A is the neutral element in the finite group. Right? This holds right, and it holds only for finite groups, right? There are infinite groups where this is not the case. And how do you show such a statement? So you basically study the order of the element A, study n. This is the order of the element A, right? And looking at this equation, if this equation holds, then A is conjugate to A square. Right? Why is it conjugate to A square? Because this is the element you conjugated with, then A is conjugate to A square. So, and that means that the order, so this A conjugate to A square, this means that n must be an odd number. Right? And on the other side, the element you are conjugating with is also conjugate to A, right? So that means if you conjugate A n times by this element, then you will recover A, right? So let me write this down. So A is of course the same as BA B inverse to the n times A BA inverse B inverse to the n. But that's easy to compute because by our relation, this is exactly e2 to the n. Yeah, because we conjugate n times, and each time you conjugate, you multiply this exponent by 2. It's kind of easy to see. So you see that altogether, a2 to the n minus 1 is equal to the neutral element, right? And since n was the order of our element A, this means that n must divide 2 to the n minus 1. And that's of course a problem, because if you take some prime number, well, since it's odd, it's, let's say, different from 2, then 2 to the prime number minus 1 will never be congruent to 0 modulo this prime number, and that's why you get a contradiction. Right, you're going to get a contradiction to the assumption that n is not equal to 1. Right? n is equal to 1, then of course it's true. Right, or let's just put it this way, n equal to 1, it's not a contradiction, twice n equal to 1. Okay, so this relation just refuses to be satisfied in any finite group without actually, for a trivial reason, that A itself is completely trivial. So you might think maybe we are able to prove that this equation, if for some permutation it's approximately satisfied, then maybe under this assumption A has to be approximately trivial. And that's exactly what you need to show if you want to show that this corresponding group is a non-sofic group. Do you have a remark? Yeah. No, that's, well, maybe I should have said this. I mean, it's a very easy, I mean, you basically construct the group so that it is satisfied. So this is just a group BA, B inverse A, B, A inverse B inverse A minus 2. This is a one-relator group. And one-relator groups are really understood very well. So in particular, you know that A is not a trivial element in this group. Right, this is a one-relator group. And right, so maybe this is a non-sofic group, right? This is like, seems at least something that one should try to figure out. And what would you have to show exactly? You have to show that if you find a pair of permutations which almost satisfies this relation, then A has to be almost trivial, right? But that's not the case. In fact, this group is sofic. And I can tell you why. And so I give you an abstract reason. You can probably construct concrete permutations that show this. So you can construct this group gamma in two steps. So first you study the Baumschlag-Solitär group. That's also a one-relator group. Let's say it's the group 1, let me write C, where C conjugates A onto A square. Right? So that's a well-known group, and it's also well known that all these two elements, A and C, they have infinite order in this group. So you can form an HUN-REN extension. Right, so this group gamma now arises as an HUN-REN extension with respect to some map phi. So this is an HUN-REN extension. Right, and phi is the map that maps the group generated by C, well, it doesn't really matter, isomorphically onto the group that is generated by A. And so what is it that an HUN-REN extension is doing? It just adds an element that implements this isomorphism as a conjugation. So you add an element, let's say B, which conjugates A onto C, and well, that's exactly what we need, right? We need exactly an element like this. And so I can now mention a few facts. I can first of all mention that it's well known that this group BS12 is amenable. In fact, it's a solvable group. BS12 is amenable, right, even solvable. And so that's the first observation. And the second is, and that's a more complicated result, the class of sofic groups is closed under HUN-REN extensions with respect to amenable subgroups. So in particular with respect to Z as a subgroup. Right, and that was, I mean, this was proved by a few different teams, I think, so in various levels of generality. So I know that there's a proof by Alec and Sabo, I think, then also Dijkema and Collins had a proof in a special case, and Liviu Paunescu, and you also, I mean, you sent me something about amalgamation over amenable subgroups. You didn't do anything, okay. Well, at least, okay, so that's so definitely means it's true, right? Many people looked at the proofs. Okay, right, and these two facts together, that implies that this group gamma is sofic, right? And so looking at the proofs, you can probably construct explicit permutations where this is almost satisfied and A is a non-trivial thing. Okay, so that's just an example that shows you that you really need some special implication like this, right? You need a very robust argument that a group has no finite quotients, and if it's robust, means that if you perturb the assumption a little bit, then the conclusion is still satisfied almost, right? And so far, we haven't succeeded to find anything like this, and yeah, in fact, maybe there are no such implications which are really robust enough to be perturbed, and so the lack of success to find such implications, I mean, maybe it also means that maybe all groups are sofic, so it's unclear at the moment. So it's really something that refuses to be, it's really not tractable. Well, I mean, it always depends on what are you really, I mean, for me it really depends on what I try to prove currently. So whenever I try to prove that a counterexample exists, I encounter that, well, there's basically no reason. And whenever you try to prove the opposite, then you see this is very difficult. So you think maybe the opposite is true, so you're oscillating. But I think, yeah, most of the people probably think it's not true that all groups are sofic just because it would be too nice to be true, right? And so there were various discouragements already over the last decades, and so people, okay, and maybe it's in fact generically not true. So if you take a random group in some sense, maybe that already fails to be sofic, but well, maybe we just do not have the right way to study them. Okay, so there's another example like this, which I want you to look at as part of an exercise. So and it's the following. So you have BA B inverse is equal to A square. So that's a relation which is a bit similar to the one here. And then you also have that A square commutes with C, and so I want you to show that, and it's not very complicated, that this also means that the A commutes with C. Right. And so there's no relationship between B and C, but still for finite groups. Right, and if you look in the literature, then most of the examples of groups which do not have finite quotients, or which have some property of like not being residually finite, they're either based on some tricks using the order, like this, so some loop basically which gives you a contradiction, or they're based on this effect, and this also can be made into an entire machinery. So for example, this effect here is also the reason why these Borger-Moses groups have no finite quotients, right? And I don't want to define these Borger-Moses groups. They are finitely presented groups which have no finite quotients, and even more, they are simple. But the fact that they have no finite quotients is related to an effect like this. And yeah, maybe that's more robust, but well, that's another exercise to show that it's at least in this form it's not robust. So you would have to like couple different effects like this to get something which is which actually works. Okay, so that's what I wanted to say about the general So do you want me to solve the exercise, or? Yeah, exactly. There's some number n that comes into the proof, and you have no control over n. Right? And depending on the size of the finite group, your computation will take n steps, or like constant times n, and so you accumulate epsilons, and there's no control, right? That's exactly the problem. But I mean, that doesn't show that it's not robust, right? But you can also give examples of permutations where you see that the conclusion is not satisfied. Right? Okay, so what I want to do now is to generalize the setup a little bit and basically try to say some things that we know about these, for example, this metric ultraproduct group that is involved here, and so I believe that somehow a very detailed study of this metric ultraproduct group should be done before one can construct a non-sofic group. So let me recall, so if G n dn, if this is a sequence of finite groups with invariant metrics, so not just left invariant, but left and right invariant, then we have defined this ultra product, which was basically the product divided by the set of those sequences that along the ultra filter, some chosen ultra filter omega, tends to the neutral element in the group Gn. Right, so let me write it like this. The distance to the neutral element tends to 0 as omega tends to infinity. Right, so what can we say about this group for particular sequences of finite groups with some invariant metrics? Right, so we have already seen one source of such finite groups. So these were the symmetric groups with the Hamming distance. But there's a very natural other class of groups which has such a nice metric, and these are the linear groups. So you have GLN over some field K. And there's also a metric which I call the rank metric. So that's how is it defined? The rank metric. It's just the rank. So it's 1 divided by n times the rank of the linear difference of G and H. Right, so that's this ambient linear space can be used to define a natural metric, and it will have exactly the same abstract properties as the Hamming distance on here. So it's another family of finite groups which has natural metrics, and in fact, once you have it on GLN, you can define a similar metric on any family of finite simple groups, right? Because they are all basically subgroups of GLN for some reasonable n. And so there's up to some constants, there's no ambiguity if you define this metric. So at least in the limit, the topology of this ultra product will be well defined, only depending on this family. Right, there's an even more abstract way of producing finite groups with such metrics. So if G is any finite group, and let's say that the center of G consists only of the neutral element, then you can define the following. You can define, first of all, well, let me right away define the distance. So the distance, and this is called the conjugacy metric. So the distance with respect to the conjugacy metric of G and H is defined to be the logarithm of the size of the conjugacy class of GH inverse divided by the logarithm of the size of G. So you normalize it in some way that it's a number between 0 and 1. And so this is my notation for the conjugacy class. Right, and it's an exercise to show this is an invariant metric. Right, so in particular it satisfies, for example, the triangle inequality, things like that. Can prove that. And so that's a natural metric which is defined on any finite group. I mean, the center, want the center to be non-trivial so that this metric never takes the value 0 unless G and H are actually equal. And the good thing is that this very canonical metric, which sort of comes to you just sort of from the structure of the group, is equivalent to these standard, more geometric metrics, which are related to notions like the rank or the count of fixed points of a permutation. Right, so they are constants so that you can estimate these metrics with respect to each other. So that's a proposition. If G is sin n or GLN over some finite field, then the conjugacy metric is equivalent in a suitable sense to the Hamming distance or the rank distance. Okay, so why is that relevant? Well, it's relevant because this is pretty untractable, this metric, right? So who knows how big a conjugacy class is in a general group? I mean, even in a general linear group, so have to compute the centralizer of an element. That's usually, well, can be complicated. So if you're down to the rank, then you have kind of, at least I have geometrically a much better intuition what this metric does. And so it's good that these are equivalent. So it's good because you can understand these metrics better. And why is it good? It's good because you know something about this metric. So there's a theorem by Liebeck and Shalev which says the following. So if G is finite, simple, non-abelian, so if G is finite, simple, and non-abelian, and then you have G, an element in G, then you can ask yourself, how many conjugates of G do I need to write an arbitrary element in the finite group G? And using this geometric point of view with this conjugacy metric, also the Hamming metric, there's of course one obstruction, right? It's an invariant metric, so if you conjugate G, its distance to the neutral element will not change. And if you take a product of K conjugates, then its distance to the neutral element will be multiplied by at most K. So just for geometric reasons, you need at least a certain number of steps to reach the other end of the group. And what Liebeck and Shalev showed is that in terms of this conjugacy metric, that's exactly true up to a constant. Right, so there exists, there exists this constant C, right, which does not depend on the simple group and not on G, such that G is equal to the conjugacy class of G. Now I'm somehow in trouble. Well, I will just write it and then I move the board. So that's obviously an obstruction that you have to, if G is very close to the identity, then you need at least like a constant times the inverse of this distance to reach the other end of the group. And what they show is that this is actually, this is the only obstruction. So once you're raising this conjugacy class to a high enough power, then you will obtain the whole group. Right? That's the result of Liebeck and Shalev. So it's true for any finite simple group. And in terms of our ultra product, this has now a very nice interpretation. So that's now a theorem. EGA is the distance from G to E with respect to this conjugacy metric, which always exists. Okay, sorry. So there exists a constant C, so that if G is a finite simple non-abelian group, G is an element in G. Okay, now I understand the question. Now let me remove this. Then this is true. Is it now clearer? Or do you want me to read this formula again, or the formula? Okay. Well, it's actually true exactly for this number, I think. Yeah. I mean, even for any number bigger than this number. So that, but it's yeah. There are some weaker forms which are also just as natural that you just look at a certain ball generated by G. But I think it's true for this exact constant. Well, equivalent means that for sufficiently small elements, but not depending on n and k, right? So if your element is smaller than, let's say, half, then these metrics are comparable with a universal constant, like a Lipschitz constant. So the conjugacy metric is like less than 5 times the Hamming distance, and the Hamming distance is less than 5 times the conjugacy metric. That's true. Yeah, okay, so I have to modify this a little bit. So this, that's true. I mean, I have to take some subgroup without center. So let's say you take PGL and you take the metric on the quotient. Okay, so that's not exactly true what I wrote here. So, yeah. PGL, and then here you have to take basically the quotient metric on PGLN. Yeah. Okay, I will. And so the theorem that you can derive from this result of Liebeck and Shalev is that all these ultra products of finite simple groups, so any metric ultra product of finite simple groups is, I mean, non-abelian finite simple groups is itself simple. Right, and in fact you can say much more from this theorem of Liebeck and Shalev. You can actually describe all the subgroups more generally, the set of normal subgroups of the usual algebraic ultra product. So that would be the product of the GNs modulo those sequences, so that Gn is equal to the neutral element on a set belonging to the ultra filter. So this is the algebraic ultra product of these finite simple groups. And for this algebraic ultra product, the set of normal subgroups, which is usually very complicated for many groups, it's very complicated, is totally ordered. So any two subgroups, any two normal subgroups, one is contained in the other, right? So you don't know which one is contained in which, but it's totally ordered. Sorry? No, I mean more generally, meaning more general than this statement, right? Because if it's totally ordered, then there will be a maximal element, a unique maximal element, and then this maximal element will correspond to this metric ultra product, and then this is a simple group. So that's why I wrote more generally, but it's not so important. So that's also a statement that you can derive from this result of Liebeck and Shalev, and it gives you some insight in how sort of sequences of permutation groups for larger and larger n, how they kind of behave if you want to study them all at the same time. And the reason is basically that there is some relative version of this result saying that if you have two elements in a permutation group and let's say the distance of one is bigger to the neutral element than the distance of the other, then you can generate this smaller element in like 5 steps or something like this. And so it must be in the normal subgroup in a very uniform sense. So do you want me to prove this lemma as a consequence of this result of Liebeck and Shalev? So it's not very complicated. So first of all, I mean, what do you have to do? You have to show it's a simple group. You have to show that every element generates the whole group as a normal subgroup. And if it's a non-trivial element in the metric ultraproduct, then its distance to the identity, it must be bigger than 0. Right? But then you can use the result of Liebeck and Shalev and see that now every other element can be written as like a constant product of conjugacy classes of this fixed element. And so basically doing this on this entire sequence simultaneously gives you that you can write an arbitrary element as a product of finitely many conjugates. Right? And this is more complicated to prove, but it's also true. Right? And so that's in the case for the metric groups, this was also already in the work of Edek and Szabo, and this fact for symmetric groups was proved by Simon Thomas and collaborators, and so we extended this to all of finite simple groups, basically relying on this result, and so this really needs a more complicated proof than what I just sketched here. Yeah, I mean, I was thinking with John Wilson about the case where you have like an extension of a simple group by another simple group, whether this goes to the limit. And so there's, I mean, some structure like this is preserved in the limit. But if your decomposition series grows, then you don't know what to do. And so the ultraproducts for these general linear groups, or the projective general linear groups, they also have been studied. And so I think Gulnara Arjantseva defined the notion of a linear sofic group to be a group which basically embeds into the ultraproduct of these general linear groups. Okay, so that's a slightly, I mean, potentially bigger class of groups, because the symmetric groups lie in these general linear groups. So whenever you are sophic in the ordinary sense, you are also linear sophic with respect to this particular field. But so we don't know whether this is a definition that really produces more examples or more interesting structures. So at least what I think is very interesting is to understand these ultraproducts and to, for example, try to distinguish them. So there's one result, I think, in this direction, which I want to mention. So this is something that showed with John Wilson. And we showed that the ultraproducts corresponding to general linear groups of different, defined over fields with different characteristic, that they are not isomorphic to each other. So the metric ultraproducts of AN with respect to the Hamming distance and PGL n over some prime p with respect to the rank distance for p prime number are not isomorphic. Right, and that's that I think is an interesting statement, because in order to prove it, you have to make a robust argument, in the sense that you have to assume that something is only true up to epsilon, and the conclusion is only true up to epsilon, and then you you can conclude something. So exactly these arguments are the ones which are missing in this strategy here. So I'm somehow feel that this is an interesting proof. PSL2, you mean, or what?
PSL2 over prime.
Yeah. Yeah. I'm sure there are. No. I mean the ultra product. So if you have like a set of primes of PSL2P, this will be PSL2 of the ultra product field, because there's right, and then it depends whether the set of primes is sort of. So it's really essential in this. I mean, if you fix the rank, then all these metrics that I've defined are discrete. So there's no metric ultra product, right? And so the ordinary ultra product of groups of finite rank, this has been studied a long time ago. They are again linear groups, but then over the ultra product of the corresponding fields, and so you run into different problems. So here we fix the prime, or we can actually also distinguish the case where the prime tends to infinity. So that's another case. Okay, so how does one do this? So how does one usually try to? How does one distinguish PGLN P from PGLN P prime if P and P prime are different primes? So basically, you look at you study elements of order P in this group, and if P is different from the characteristic over the field, then there's some special behavior, and if it's equal to the characteristic, you find some unipotent elements. Okay, so let P and Q be different primes. So then any element of order P, let's say in GL and Q, is semi-simple. So that means over the algebraic closure, this matrix is diagonalizable. Yeah, and if it's diagonalizable, then you have you can study the eigenvalues, and in particular, if you look at the centralizer of this element, then this will again be a product of groups like this, right? So the centralizer in this group G, let me just write, did I give this element a name? So the G, let's call it G, the centralizer is a product of at most basically P. It's not exactly a product, it's like a central product of quasi-simple groups, but you can think of it really as a product of a product of at most P basically simple groups. So that's exactly what will be true in the ultra product then, right? The limiting statement. Okay, that's if P is different from Q, and so now if you take an element of order P in GL, let's say 2n P, right? But the element 1, 0, right? This is now an element in GL 2nP is of order P P, and it's not semi-simple. Right, in fact, I have written down its non-trivial Jordan decomposition already in this form. So you can now again look at the centralizer. And so the centralizer of this G, it will be an extension of some simple part which centralizes basically these diagonal matrices, and then there will be a large abelian part of the form identity something here and identity here. This will also commute with this matrix. Right? The centralizer will contain a large abelian group, which is exactly the n by n matrices with respect to addition sitting inside. So if you have a matrix A, then you just view it as an element in the centralizer, mapping it to the upper right corner. Right? So it's from the group theory side, it's a completely different phenomenon. So whereas here you have basically a product of simple groups, you have this part here also, but you have this huge abelian normal subgroup on which there's a non-trivial action effect of the simple part that you also have. Okay, and basically what we show with Thom Wilson in the proof of this theorem is that exactly this phenomenon, this can be epsilonified. So if you look at the epsilon centralizer, if you look at all the epsilon elements that commute with an element of order P up to some epsilon, then they will be still of the form up to some other epsilon, right? Some delta say. And exactly the same phenomenon happens here. So the problem is, so this argument allows me to distinguish, to recover the prime basically from the group structure. That's no surprise. So now I want to do the same for the ultraproduct. So I look at an element of order Q in this ultraproduct. So I first do some tricks to produce a sequence of elements of order Q in the GLNs. But if I want to describe the centralizer in the metric ultraproduct, then I have to look at sequences which better and better commute with this sequence of elements of order P, because only in the limit you really want it to commute. So you have to do the same argument, but instead of looking at the exact centralizer, you have to, well, pick some epsilon and say you want to study the elements which up to epsilon commute with G. And you want to understand the structure of this set. And, well, that's now some trick that you have to do, and so you should be careful. The trick should not depend on n, right? It should be like a uniform trick in some sense, to see that any element in the centralizer is in fact close to an element in this product of quasi-simple groups. And the same with this argument. And this exactly shows you that in this ultraproduct there's an element of order P which has this huge abelian part in the centralizer, whereas if you have an element of order P in the ultraproduct of these groups, there's no such element. Right? So the group structure tells you back with what prime you have started your construction. Right? And in some sense, so whereas for these groups there's exactly one prime with bad behavior, so that allows you to recover the prime. For these groups, all primes behave in a bad way. Right? If you look at the centralizer of an element of order P here, you can have this phenomenon many times. For all P, you can have that by looking at a suitable element of order P. Right? So that's the sketch of the argument. Right? Of course, I didn't tell you anything of the, I didn't tell you the crucial part, how you do this with the epsilons, but, well, it's a little bit too complicated to do this at the blackboard in the given time. So at least these groups are not isomorphic, and so it's an interesting question, I think. To find out what happens for the other families of finite simple groups. Right, so do they give, yeah?
What would you say?
Well, I would say that this phenomenon that you have an element of order p which has a large, almost centralizer which is abelian, this can only happen in if your characteristic is p. Yeah, that's more complicated, so we don't know how to distinguish p from p square. Maybe there's, I mean, we didn't think for a very long time about it, so maybe that's possible. Okay, so what happens for the other families of finite simple groups? So that's exactly going in this direction, where you have like a prime power that arises in this construction, or you have like a different type. And so one should be a little bit careful, because we are looking at this only up to small rank. For example, the even orthogonal groups and the odd orthogonal group, that actually makes no difference, right? So there are some collapse of these families, and there's also some reason to actually believe that also the symplectic groups should be in the same family. But I mean, at least in characteristic 0. So I mean, I don't know. It's kind of it's not so obvious what actually happens exactly. Well, then the ultrafilter helps you, because the ultrafilter will always select, so there are only finitely many families. It will select one family, and out of the primes, it will select one prime, or the prime tends to infinity, right? So there are only, and so these cases, say, we can all reduce this to somehow to these more canonical cases. Yeah, let me think. So what else do I want to say? So what happens for these other families of simple groups? So this is what I just remarked. So this is up to rank 1, right? These are the same group, so the ultraproducts will not see the difference. But for example, I'm very confident that the symplectic groups, for example, they should be different from the projective linear groups, maybe using a similar argument, but so we have not done this. And so, okay, that's one thing that one would like to study. And then these metric ultraproducts, because they inherit this metric coming from the definition, basically, they themselves are topological groups, so it's very natural to study their properties, right? So are they totally disconnected? Are they maybe connected or simply connected? All these properties. I mean, this all should reflect, of course, asymptotic properties of permutations, but it's not so obvious how these topological properties, I mean, how you reformulate them. So there's one result that we have in this direction, which says that so the ultra product, so that's again the metric ultra product of alternating groups with their Hamming distance is actually a geodesic metric group. And what does that mean? So that means, by definition, for all G and H in this ultra product, there exists a continuous map from the not the unit interval, the interval from 0 to the distance between g of h into the cube, so that's the metric ultraproduct g omega, and that's an isometric, in particular it's a continuous map, but it's isometric, so it preserves distances with phi of 0 equal to g and phi of the other end of the interval equal to h, right? So that exactly says that there's a geodesic connecting the 2 points, right? And so that's from, once you have a metric cube, that's a very natural thing to ask, right? And if you translate it back to permutations, it's, well, not so natural to ask anymore, but it's true. And so, for example, what we don't know, what would be very interesting, is whether this cube, which is now obviously connected, is also simply connected, right? So if you have a triangle of geodesics, let's say, can you fit it in with a geodesic triangle, right? Can you do some like approximate metric geometry on permutation cubes, right? So in the limit, things kind of, all the things are smeared out, so you have continuous objects, so some questions are more natural to ask. And so that's I think an interesting subject in itself, to understand these groups as metric spaces. And for the linear groups, for the, let's say, projective linear groups, I mean, there are certainly notions of curvature for metric spaces where you look how geodesics, I mean, but it's not a unique geodesic space, first of all. Even on small scales, there are many geodesics. So it's a bit more complicated. And so we believe that this is also true for the other families of finite simple groups. So for the moment, I think we only have this for the alternating group. And for the general linear group, we at least know it's a connected group, but we don't know whether it's actually so nice that everything is connected by a geodesic line segment. Okay, so there are many questions about the metric geometry that one can ask, and so I don't think that they have been asked. So maybe that's also good for the students here and for people that want to get into this subject. So because it's probably difficult to set yourself a project, construct a non-sofic group, maybe it's easier to work on some problem which is more tractable and it's in the same area, so that you could understand these groups which play this crucial role here better, and maybe one day the geometry of these groups is understood well enough so that we can use this information to produce a non-sofic group or not. Okay, so I think I'll stop here and thank you for the attention. So any questions? Well, I mean, it's really a local condition. So if any finitely generated subgroup is sofic, then the big one will be sofic, so there's no real need to. But for example, this second definition that I wrote, where you have these maps psi defined on the gamma itself, this definition just makes sense for any group. So it's just pointwise convergence, so you. Any more questions?
Last year,
I mean, I have to say it's not difficult to prove this result. So you take a permutation and you basically have to find another one that looks on half of the space looks like the permutation, and on the other one it's trivial. So it's once you ask the question and you translate it back to the right finitary statement, then it's not complicated to prove. And I think many of similar kind of statements should be of the same form. But still, it seems to be fundamental. I mean, and it's only the first step, so I think interesting structure. Okay, so we can... No, they are not compact. They are far away from compact. Yeah, I mean, they have infinite discrete subgroups. So any sofic group will be an infinite discrete subgroup.